Let's see now how we compute the steady state distribution of a Markov chain that is positive, recurrent, and irreducible. By the way, when the Markov chain is positive, recurrent, and irreducible, we usually say that the Markov chain is ergodic. Okay, so let's say that we've got Qij, where ij belongs to the state space, and Qij is the speed or the rate of the transition between I and j. And we assume that I is different from j, okay, because we can't have in continuous time setting a transition from a state to itself, and Qij is greater or equal than 0, where if it's 0, it means that there is no transition from I to j. So to compute the stationary distribution, which is pi I, okay, for all I belonging to S, okay, remember that pi is the limit for t that goes to infinity of the probability that my Markov chain x of t is equal to I, and we can ignore the conditioning on the initial state because we are under the assumption that the Markov chain is ergodic. Okay, so to compute pi I, we need to balance the flow outgoing from the state and incoming to the state. So if this is state I, the state I will have some transition going to some other state, and the flow outgoing state I is pi I times the sum for j in S and j not equal to I of q from I to j. So basically it's the flow of this arrow here would be pi I times its rate. The flow of this arrow would be pi I times this rate, and the flow on the third arrow would be pi I times the rate of this third arrow. Okay, but we can group pi I, and so you got this formula here. So this is the outgoing flow. Outgoing flow. The incoming flow to state I, okay, is equal to the sum for j in S and j not equal to I of the pi of this state, which is pi of j, times the rate of this transition, which is qji. Okay, so this equation here, where the unknowns are pi I and pi j's, are called global balance equation equations of the system of the Markov chain. Okay, and of course you may observe that this system of equation is satisfied for pi I equal to 0 for all I, but in fact we need to add another condition, which is the normalizing condition, which is the sum for I belonging to S of pi I must be equal to 1. So this is the normalizing condition. We can rewrite these equations in matrix form, and we begin with the matrix of coefficient that is usually called Q, and this is called infinitesimal generator of the Markov chain. So matrix Q has the entries which will be Qij, okay? And Qij is simply equal to our small qij if I is different from j, but this is equal to minus the sum for j belonging to, so for L belonging to S of qij IL if I is equal J. So basically we can imagine Q as a matrix that has a diagonal with negative elements, and the elements that we have in row I and column J is the rate of the transition from I to J, but the element that we have in position I is the sum of the extra diagonal element of row I with the opposite sign. Okay, so in matrix Q, all rows sum to 0. Okay, so this is how it's done, the infinitesimal generator. And then you may observe that the steady state distribution, the vector pi, which is a row vector, can be multiplied by Q, and you must get a vector of all 0, and you must have the normalizing condition that pi times 1 must be equal 1. So this is going to be a vector, this is going to be a matrix, this is going to be a vector, and this is going to be a vector. Okay, row vector, column vector for 1, and then you have here is a row vector for pi, and Q is a square matrix. Okay, if by the way, if the Markov chain is ergodic, you have a unique solution to this system of equations. Let's try to see how we can solve the birth and death process. So we got 0, 1, 2, 3, and 4, and so on. And for simplicity, we put constant birth rate and constant death rate. So here we put lambda, and here we put mu. So let's write down the balance equation for state 0. So we have pi of 0 multiplied by lambda must be equal to pi 1 multiplied by mu. So this equation is this flow here, while the second equation is this flow here. Okay? If we write it for state 1, then we have that pi 0, and here I have to sum lambda plus mu, which is the outgoing flow from state 1. Sorry, this is pi 1. This must be equal to pi 2 times mu plus pi 1, pi 0 times lambda, which is the incoming flow to state 1. In general, when you got state n, you get pi n lambda plus mu is equal to pi n minus 1 lambda plus pi n plus 1 mu. Okay, and this keeps going on. Now we can solve this system by supposing that we know pi 0. So suppose you know pi 0. Okay, then you get that pi 1 from the first equation is equal to pi 0 lambda over mu. Okay, then you take this expression that you obtain here and you plug it in the second equation, the one for state 1, and you obtain pi 0 lambda over mu times lambda plus mu is equal to pi 0 lambda plus pi 2 mu. Now the only unknown that you have is pi 2, so you can explicit pi 2, and this is equal to pi 0 and here you got lambda over mu times lambda, it gives you lambda square over mu plus, and then here you've got lambda over mu times mu gives you lambda, then here you bring on the left hand side pi 0 lambda, so you got minus lambda. Okay, and all like this is 1 over mu, so plus lambda minus lambda goes away, and this means that pi 2 is equal to pi 0 lambda over mu squared. If you keep going on in this way, now you use pi 0 lambda over mu squared to in the equations for 2 for the second one, you can obtain pi of 3, and pi of 3 will be pi 0 lambda over mu cube. In general, you get that pi of n is equal to pi of 0 lambda over mu at the power of n. Okay, we're not done because we're assuming that we know pi 0, but we actually don't know pi 0. So let's go, just to simplify the notation, lambda over mu equal rho, and let's call rho will be called the load factor of the Mn1 cube. So we remember that we have another equation that has to play a role, which is the normalizing condition. Up to now, we only used these equations here. We have never used the second one. So we want that pi 0 plus pi 1 plus pi 2 plus, this must be equal 1. Okay, so basically we want that the sum for n that goes from 0 to infinity of pi 0 lambda over mu at the power of n must be equal 1. And at this point we have only one unknown, which is pi 0, that can be brought outside the sum, and so you get pi 0 sum for n that goes from 0 to infinity of lambda over mu at the power of n, and this is equal to pi 0 sum for n that goes from 0 to infinity of rho at the power of n. This is a geometric series, and it converges if and only if rho is lower than 1, that is lambda lower than mu. Again, here we have the stability condition of the Q that comes up. So under this condition, this is equal to pi 0 times 1 over 1 minus rho, which is the convergence of the geometric series. This guy over here must be equal 1. Thus, we got that pi 0 is equal to 1 minus rho. Okay? And this means that now we have the entire solution of our birth and death process, because we got that pi of n is equal to pi of 0, which is 1 minus rho at the power of n. And this, we recognize it as a geometric distribution. Okay? And this is an example of solution of the global balance equation of a system.